Okay, thanks. So it's my very pleasure to introduce Andres Moreno Spina from Institut Camille Jordan, University of Lyon, who will talk about a parabolic flow for large volume heterotic G2 system. Please.
Okay, hello everyone, and thank you, Beatrice, for the introduction, and also thanks to the organizers for the invitation to give this talk today. So this is a joint work with Mario Garcia Fernandez, Alec Payne, and Jeff Streets, which is available in Archive. So the idea today is going to be to try to explain the new geometric flow of G2 structure that we introduce in order to try to study solutions for the heterotic G2 systems with large volume, which also uh, have been studied with another name. We saw that in some talks previously, known as G2, strong G2 with torsion structures. So the idea for this talk is to give some background on G2 structures and torsion and geometric flows of G2 structure, which some of these things have been seen before here. So sorry for the repetition, but it's just in order to try to fix some notation. And then in the second part, we are going to try to define this heterotic G2 flow. I will try to explain the issues that we found trying to define a good flow. And for a good flow, I will mean a flow with short time existence and uniqueness, and also preserving the right torsion class and getting also the a nice critical points. And finally, I will also mention some analytic results, in some sense related with questions related with long time existence, and also an application of this flow to the dimensional reduction when the seven manifold is some manifold with an SU3 symmetry. So as we almost everyone knows now, G2 structure is going to be a differential 3-4, which can be identified with the standard G2 structure on R7, which is coming from the product from the octonions. So you can write this 3-4 in a base in this nice way. And using this 3-form, you can define the G2 structure as the stabilizer of this 3-form inside the general linear group of R7. And so you will define a G2 structure on your manifold as I say, as a differential form, which at each point you will have a frame of your frame bundle, at least a local frame, which can be identified with this standard 3-form. And because of the dimension reasons, the bundle of the G2 structures is an open bundle in the bundle of 3 forms. So the nice thing in this kind of geometry for G2 structure is that when you have this 3-form phi, you can recover all the Riemannian geometry for your manifold. So you can describe the Riemannian metric, the orientation in a nonlinear way, given by this relation. And of course, because of this, you can also define the Riemannian connection, the Levi-Civita connection, and the Hochstar operator. And with this Hochstar operator, we also have a very important tensor, which is the dual, the Hoch dual of the 3-form, this 4-form psi. And we say that the manifold is a G2 manifold if the tree form is parallel with respect to the Levi-Civita connection induced by the G2 metric. And because of the holonomy principle, this condition means that the holonomy of the corresponding Riemannian metric is contained in the group G2. So the main problem, of course, in G2 geometry is trying to construct these examples, these G2 manifolds. But the condition is a nonlinear PDE, so try to solve this kind of equation is very hard. So that's why you can decompose this condition into a linear condition, which is the exterior derivative of phi, which is the closed condition, and a nonlinear condition, which is the exterior derivative of psi, which is called the closed condition. And you get that these two conditions are equivalent with the condition of being parallel, what we call torsion-free. So in order of this decomposition, you can study the reducible decomposition of the space of differential forms. So for instance, when you have the induced G2 action in two forms, you have the decomposition in 7 dimensional reducible subrepresentation, which is associated with the standard representation of G2, and a 14-dimensional subrepresentation, which is associated with the Lie algebra representation of G2 coming from the adjoint representation. And you have the same thing for the space of three forms. So you have a 1-dimensional irreducible component, a 7-dimensional irreducible component, and a 27-dimensional irreducible component. So, and you get all the other space of K forms just by the Hodge star operator. So with this decomposition, you can define the torsion forms, which is basically each of the components of the exterior derivative of phi and the exterior derivative of psi in each irreducible components. So you have tau naught, tau 1, tau 3, and tau 2. So, oh, sorry. So with these 4 torsion forms, you have in total 16 classes of G2 structure with respect to the torsion. So as we saw before with the Fernandez-Gray theorem, is that the torsion free is equivalent to the vanishing of all torsion forms. But also you can study some weaker conditions for the torsion, as for instance, the nearly parallel G2 structures, which means that psi is closed, but phi is proportional to psi. So you just have a 1-dimensional component of the 4 form. Or you can study the closed G2 structures, which means that phi is closed, as we said before, and the analogous, which is the co-closed condition. Each of these class has some particular properties. For instance, nearly parallel G2 structure induce Einstein metrics, and closed G2 structures, they are very rigid in the sense that the scalar curvature is strictly negative and exactly 0 if the G2 structure is in fact torsion free. And for instance, co-closed G2 structures are generic in the sense that, as was proved by Crowley and Nordstrom, if you have a G2 structure, you can always find a co-closed G2 structure in very close to this initial G2 structure. So in some sense, you can deform always continuously a G2 structure to obtain a co-closed G2 structure. But as I say, these are just some classes. The class that we are interested in today is the class of integrable G2 structures, which means that the torsion form tau2 vanish. And as I said before, the one geometric property of this torsion class is that there is a unique linear connection we call Nabla-Plus with total skew symmetric torsion that makes parallel the G2 structures. So in particular, this connection, which is a connection with torsion, has also holonomy G2. And when the torsion vanish, this connection, of course, coincides with the Levich-Vita connection. So you have a G2 manifold in that case. So we are, as we say, we are interested to study this kind of G2 structure today because the following motivation, and it's because we call a G2 structure as an integrable with closed torsion if it satisfies the integrable condition, which means that the exterior derivative of psi is equal to 4 times tau1 wedge psi, and also the torsion of the connection with total skew symmetric torsion is closed. We saw in the previous talk of UDAF that this is called also a strong G2 with torsion. So in particular, these G2 structures are motivated by generalized geometry, as was studied also by Agnaldo da Silva, Garcia Fernandez, Lotey, and Saer. They proved that if you have this kind of G2 structures, in fact, the torsion tau naught is exactly a constant, is no longer a function. And this constant describes exactly the generalized scalar curvature, which is another quantity in generalized geometry. So some motivations to study this kind of G2 structure is that if you are in some particular setting, as for instance in a compact manifold and tau naught vanish and tau1 is exact, the integrable condition and the closed torsion condition is exactly equivalent to the torsion-free condition. For instance, in the non-compact case, if you have that tau0 is 0 and tau1 is 0 also, which is also called as a purely co-closed, the closed condition for the torsion means torsion-free. So in some sense, this kind of structures, when you have some particular torsion and the vanishing of this torsion-free form, could be a way to find torsion-free G2 structures. Also, there is some other motivation to study this kind of G2 structure, which is motivated by, as I said before, by generalized geometry. Basically, it becomes from the fact that if you try to look at the composition of the exterior derivative of H5, and you look at each irreducible decomposition of the space of 4 forms, which the first line here is given by the component in the 1 and the 27 component of 4 forms. And the second line is the one related with the 7 part of 4 forms. So when H5 vanish, this condition is equivalent with these two equations, which are known as generalized Ricci-Soliton equations. And also, of course, another in the case of compact.
Sorry, Andres,
And when you,
can I ask you a question?
yep, yeah,
So,
sure.
when you say, okay, if dh phi is equal to 0, then you have this Ricci minus h squared plus the derivative of g, and then you have this
Yeah.
other piece. So
Yeah.
so if you impose 0, then the first is 0, but why don't you have some condition on scalar curvature, or this is just a trace of the first?
Yes, that is one that is one of the issues. As I say at the beginning, trying to define this good flow and all these things, we found some issues. And the thing is that, of course, as I will say later, we wanted to evolve by something given by dH. Our flow supposed to be something like this. But if you have a flow of G2 structures evolving in this way, the first line is going to determine the evolution of the metric. So for the evolution of the metric, you will have this other part that you mentioned. But
Okay.
so you won't evolve by generalized Ricci flow. But this term vanish is because that term is exactly the one-dimensional component with a different factor. This 1
Okay.
over 8. So yes, if vanish each component, the 1 and the 27-dimensional component vanish independently, but at the end you get the same equation for the static condition. Yes.
Okay. Thank you very much.
No, thank you to you for the question. And also, I mean, something also related with your question is, of course, this second equation in the generalized Ricci-Soliton is the skew-symmetric part of the Ricci of Nabla+, the vanishing of the Ricci Nabla+, the skew-symmetric part. So if you look at the skew-symmetric part, the skew-symmetric part is a two-form, and we saw that a two-form decomposing the 7 part and the 14-dimensional part. But then when you try to extract, but there is no 14-dimensional part in 4 forms, and there is just a 7 part because the 14-dimensional part is in the kernel of this diamond action. So we can write this equation in the whole, I mean, as an skew-symmetric equation, not just the 7 part, because the integrable condition makes that the 14-dimensional part of the second equation vanish. So yeah, for instance, we would like to ask, if you don't have the integrable condition, what happened with dH phi and what happened with the 14-dimensional component. And some digression, as I put here, some remark, which is something which is not in our paper, but it was a discussion at some point with Mario, Jeff, and Alec, is that if you can try to write the some general relation for the Ricci tensor of Nabla+ for dH phi, and look what is the measure of these two quantities when the G2 structure is not integrable. And that is given by the right hand side of part of the equation, which is this pi 7 of R+, which means the projection on the 7 part of the two form of the tensor curvature of Nabla+, and this other contraction of Nabla plus psi with this 3 form H phi. So of course, if this guy in the right hand side vanish, you will recover the the left-hand side equal to 0, which is basically the Ivanov-Stange formula for DH5. And when you look this equation equal to 0, which is a second-order equation in Nabla, given by the connection Nabla plus. When this vanish, these two tensor vanish, if you take the trace, for instance, what you get is that the north of tau2 vanish. So in some sense, this other term is hiding the condition of being integrable of tau2 vanish. Okay, so maybe to study this operator pi 7 of r plus this other lower term could be another way to try to study integrable G2 structures and see or moreover if there are some other conditions to have closed torsion. Okay, but so finishing this digression, so what we wanted was to study to introduce a geometric flow, preserving some torsion class, probably hopefully the integrable condition. We wanted also that the integrable, the critical points were integrable G2 structure with closed torsion, at least. And of course, the more important property, that the geometric flow has short time existence and uniqueness. So before I introduce the flow that we propose, I would like to make some visiting some well-known G2 flows. Perhaps the most famous is the Laplacian flow introduced by Bryan, which means that evolving your G2 structure by his Laplacian. So in the compact manifold, the critical points are the ones given by closed and co-closed. So the critical points of these are torsion-free in the compact case. And so it was proved by Bryan and Zhu the short time existence of this flow and uniqueness. And they also found that if you evolve in the cohomology class of the initial condition, so if you evolve with the initial closed G2 structure, the flow is going to remain, the flow solution is going to remain closed. And also you can interpret this Laplacian flow as the gradient flow of the volume functional, the Hitchin functional, restricted to the cohomology class of the initial condition. And this very nice property was exploited by Lotey and Wei in several papers to get some very nice analytical results as sheet-type estimates, so higher order derivatives of the torsion and the curvature in order to get some results related with compactness, stability of the critical stability of solutions of torsion-free G2 structures and the critical points of the Laplacian flow. So the study of the Laplacian flow has been very fruitful. So at some moment, Karigiannis, McKay, and Zhu, they introduced the analog of the Laplacian flow, which is called the Laplacian coflow, which means in a very natural way try to evolve the fourth form psi by his Laplacian. You can also make the same interpretation as in the Laplacian flow. The critical points are going to be torsion-free G2 structures. And also you can recover a gradient flow interpretation of this flow when you restrict to the cohomology class. But the problem was that this flow has no short time existence and uniqueness. At least they were not able to prove this using the classical techniques from the Ricci flow. So a way to overcome this problem was proposed by Sergei Grigoryan with the so-called modified Laplacian coflow. Basically, the idea was to add some exact term to the Laplacian coflow in order to kill the bad directions in the linearization of the Laplacian and in order to get the parabolicity for the flow. So the way as I wrote the modified Laplacian coflow is in a bit general way as was done by Grigoryan, because he just took this C, a particular constant, I think it was 2. But I put this constant in a general way in order to try to make some relation with our heterotic G2 flow later. But so as I said before, doing this modification, you can prove a short time existence for this modified coflow. You can also have some kind of monotonicity of the Hitchin volume functional along this flow if you have some bounds for tau naught. But the problem now is that you don't have any description for the critical points for this flow. So for instance, as was remarked by Jason Lotte, is that now, for instance, a nearly parallel G2 structure, which means that you have tau 1, tau 2, and tau 3 equal to 0, is now also a critical point for the modified coflow when you take this particular value of A. So in some sense, the modified Laplacian coflow maybe is not good if you want to find torsion-free G2 structures. But also, now you have these new critical points, which are the nearly G2 structures. And it was proved also by Kennan and Lotte, and also in another paper with Jacob Stein, that for a very particular ansatz of nearly G2 structures on Fisa-Sakian manifolds, the canonical nearly parallel G2 structure, which can be constructed in these manifolds, are stable in the case of the Laplacian coflow, but they are unstable in the case of the modified Laplacian coflow. So in some sense, the Grigoryan modification solved the problem of short time existence, but then it also brings another problems to the flow as this instability of the critical points. So as I said before, in some sense, we want to evolve our G2 structure in the direction of minus DH5 in order to get the critical points as G2 structures with closed torsion. So it was proposed by Ashmore, Minassian, and Proto this flow evolution for psi coupled with this function phi. And if you started with this close condition, sorry, this F should be little phi, but it was a typo. So if you start with a close condition, because you are evolving e to the minus 4 phi psi by an exact 4 form, the close condition is going to remain along the flow, which means that the the flow lines are going to be G2 structures with integrable G2 structures, and in particular, tau 1 is going to be exact. So if you try to apply this flow, what you find immediately is that this flow, this Ashmore flow, is going to be basically some kind of modified Laplacian coflow up to this gauge term given by the derivative of the gradient of phi, and this little phi I will going to call the dilaton. So if you want to look at the short time existence, you see that exactly the coefficient that you get is not in the range that Grigorian found for the short time existence of the modified coflow. So you have no short time existence for this equation. So something that you can try to do to overcome this problem is to apply the same Gregorian modification, and now with C in an appropriated interval. But now the first thing that you look is that if you evolve the G2 structure in this way, the induced evolution for the metric is going to be by some kind of modified generalized Ricci flow. And as was remarked by Beatrice at the beginning, you will have this scalar curvature terms, which is basically this inner product of dh phi with psi. And you can try to you can try to kill this term, for instance, taking some particular evolution of the dilaton. But the problem is that this middle term, you will always have something which is non-diagonal. So you never take out this term in order to get some evolution by generalized Ricci flow. Of course, different from C different from C, C different from 0, which is not the constant that we want to take, because we know that the flow has no short time existence. So you have this issue, but of course you still have the degree of freedom of what is going to be the evolution for the dilaton. So what we propose as an evolution for the dilaton was this modified heat type equation for the dilaton, where the lower order terms are corresponding with the torsion of the G2 structure and the differential of the dilaton. And for this family of equation given by any parameter gamma and sigma, we can recover many properties for this coupled flow. So for instance, if you fix lambda, gamma and sigma by this quite weird constants, the right-hand side of the dilaton flow becomes exactly by the one component of dh phi. So what you can prove is that in this case, for C different from 0, the critical points, if you have a critical point for the coupled flow, for the evolution of psi and the evolution of phi of the dilaton, you get these critical points, which means that in the compact case, as because of the remark that we did in the beginning, they are exactly torsion-free G2 structures, and the dilaton is going to be constant. But this property is just for one particular choice of these parameters. So we can try to look if there are other interesting choices for these parameters. And that is something that we found when we studied the so-called G2 dilaton functional. So basically, the G2 dilaton functional is some scaling of the volume functional, which is very similar with the dilaton functional study for the SU3 structures. So if you study the first variation of this functional in the cohomology class of some four form, which we call the balance class. If you study the first variation of this functional, what you find is that the solutions for our coupled flow, the heterotic G2 flow, with initial conformally co-closed initial condition, if the parameters have these bounds, we found that the functional is non-decreasing and is going to be constant exactly for torsion-free G2 structures and constant maps. So we have a large choice of good parameters to study some very good properties of these functional along flow solutions of our flow. So with these properties and this characterization of the critical points, we can state our first result, which is the short time existence for our heterotic G2 flow. So for any initial conformally co-closed G2 structure and taking C bounded by -1/3 and any parameter gamma and sigma, we have that this flow has solution for short time, and the solutions are always conformally co-closed G2 structures. So some remark is that a similar flow was studied also by Karigiannis, Picard, and Swan. They also study a flow of conformally co-closed G2 structures. I tried in their paper, the flow equation is written in a quite different way. I tried to write in our notation the flow, and in our notation that flow is going to be as given in this. So in some sense, the C is a translation of our C, constant C. And the difference is that the dilaton is constrained by this volume condition. So this constraint of the volume means that the dilaton is going to evolve by exactly this equation, by -1/4 the trace of S, where S is the symmetric tensor describing this four form. So in some sense, the evolution of the dilaton in this flow can be recovered using some very particular parameters of gamma and sigma. But for instance, I don't know if this dilaton evolution is in the range of our flow that makes the G2 dilaton functional monotonic about along the solutions, for instance. That is something that I don't know. But just to make this remark about this other paper. So okay, so having a short-time existence, we would like to ask when there are long time, when the solution can be extended for long time. So for that, as in the Ricci flow case, what you need to do is try to
And
look how.
can I
Yes,
ask you another question? In the
sure, yes.
Karigiannis flow, the static point are again torsion free or not?
No, it's not clear for me. because
Okay.
because for us the torsion-free the torsion-free critical points they depend exactly of these lower order terms given by the gamma and the sigma ones.
Mhm.
So in that case, I don't know. I don't know. I don't think
Okay.
because they are just this parameter C. This parameter C is basically the parameter introduced by Gregorian, and as far as I know, in the Gregorian case, you don't have these critical points.
Okay, thank you.
Okay. So if you want to study long time existence, some natural thing that you should try to do is to look how is the evolution of the geometric quantities related with your geometric tensor. In this case, how is the evolution of the Riemann curvature tensor? So because the metric is evolving by Ricci plus this gauge term plus lower order terms, which I describe as T star T, which is basically some kind of contraction of your torsion forms in order to get a symmetric tensor. So what you find is that the evolution of the Riemann tensor is going to be quite similar as the evolution of the Ricci as the evolution of the Riemann tensor in the Ricci flow up to lower order terms. So what you find is that the higher order terms is basically the Laplacian of the Riemann tensor. The other ones are lower order. And you can do also the same thing for the intrinsic torsion. So what you find is that the intrinsic torsion is going to have some very similar behavior. One of the leading terms is going to be the Laplacian of the torsion, but then you will have this other term, which is the Hessian of this torsion tau naught. And then you can make a very particular choice of the constant C, which is inside the range that we found for the short time existence, in order to get some kind of heat type equation for the torsion up to lower order terms, in order to try to apply the maximum principle and get some estimatives for these quantities, which is basically what we want in the sheet type estimate. So you just try to apply uh, some inequalities for this choice of the value C. And what you get is some inequalities for these quantities and using some inequalities you can apply the maximum principle in order to get some estimates, which are called the sheet type estimates, which basically it says that if you have a solution for your flow in short time, in this case, it's stated in the local sheet type, but for instance, it also is also true for the compact case, for compact manifolds. So if you have some bound on this quantity lambda, which is basically some bounds in the curvature, bounds in the torsion and the first derivative of the torsion and in the dilaton, if you have these bounds for any time of your solution, you can find some other constant depending of the limit time of the solution and all the constants that we have involved in our flow in order to get some bounds for higher order derivatives also for the dilaton, the curvature, and the torsion. And the important application to these sheet type estimates is this very nice result, which is the convergence of solutions when you have uh, some hypotheses. So, for instance, if you have again these bounds in the curvature, in the torsion, and the first derivative of the torsion and the dilaton, it means that you can apply the sheet-type estimates, and if you can apply the sheet-type estimates, because of the short time existence, you will have a solution for short time, and the sheet-type estimates is going to allow you to extend the solution a little bit more. In some sense, you can extend, if you have these bounds, using the sheet-type estimate, you can extend the flow onto the infinite. So you will have long time existence. And then using these other bounded quantities, which is the injectivity radius of the manifold and the volume, also the volume, the diameter bound for the metric for each time. You can also have some bounds for the G2 dilaton functional. So it's going to be bounded below and bounded above. So using this bound and the monotonicity that we have for this particular choice of gamma and sigma, you can using the compactness theory, I think can be also do if using the compactness result, which is also obtained in the paper of Lotay and Wei. You can extract a subsequence which is going to converge to a torsion-free G2 structure, which are the critical point of the flow. So just to finish, some applications to the dimensional reduction of our heterotic G2 flow. So if you have an SU3 structure, you can do the same thing as in the G2 case. You can describe your G2 structure in terms of the torsion forms. So these torsion forms are more now than in the G2 case. You have 7 torsion forms, which describe each component of the omega, d rho plus and d rho minus. Rho plus is the real part of the complex volume form, and rho minus is the imaginary part of the complex volume form. So in particular, if you have these ansatz for a G2 structure, which is the most general S1 invariant G2 structure, giving us a tree form in the total space of S1 bundle over a 6 manifold with SU3 structure. You can try to ask what is the integrable condition for this S1 invariant G2 structure in terms of the connection one form and in terms of the torsion of the SU3 structure and in terms of the function. So what you find is that the integrable condition is equivalent to this PDE in terms of the differential of this of H, the torsion forms nu1 and pi1, which are related with the Lie derivative, with the Lie form of the SU3 structure. And you need that this sigma 2 is equal to 0. So then doing some computations, you can compute tau naught and H5 in this very general setting, which is quite known, very nice. But then if you try to make some hypotheses, like for instance, this function H is constant and the connection one form is SU3 instanton, what you get is that for instance, the 3 form H5 simplifies. So it's going to be H omega, which is basically the corresponding 3 form of the corresponding torsion 3 form of the connection that makes parallel the SU3 structure, or at least the candidate to be. And we have that if you have an integrable G2 structure, an S1 invariant integrable G2 structure under this hypothesis, theta and SU3 instanton, and also pi2 is equal to 0, which is one of the other torsion forms of the SU3 structure. So the closed condition for H5 is related with some, basically with the heterotic Bianchi SU3 identity for the SU3 structure and the connection 1,4. So now, doing the same thing, you can try to write the flow equations. So what you get for the flow equation for the SU3 structure when you run the heterotic G2 flow for this S1 invariant G2 structure is this coupled system of equations, which is also very general, but something that you can see is that, first of all, in this setting, we are not in the integrable setting, as in it means that integrable in the sense that the almost complex structure is not integrable. So that's why you will have distortion components that describe the Nyhus tensor. In this case, one of them is pi 0. So that's why the first equation is like some modified anomaly flow in the non-integrable case. And the second equation, which is a flow equation for rho minus, for the imaginary part, is also some modified equation by this also, again, by pi 0. And this equation consists up to modification with a flow of type 2A, with the type 2A flow. So what we found is that up to this modification terms given by pi 0, the coupled equation is some interface between the anomaly flow, which is the type 2B flow, with some other modification of the type 2A flow. So some interesting question could be try to see what happened with the evolution of pi 0 along this flow. So if, for instance, what happened if you start with pi 0 equal to 0, if this condition is preserved, and then you will have some coupled type 2A and type 2B flow. Okay, so many thanks for the attention.
Thank you, Andres, for the nice talk. So are there any questions, comments?
Hi, can I ask a question? Can you hear me?
Sure.
Yeah, sure. Hi, Mateo. How are you?
Yes. Hi, Andres. I'm good. Thank you. Thanks a lot for the nice talk. It's very interesting.
Thank you.
I was wondering, so yeah, I thought it was very interesting, this reduction result, like this way to reduce like this kind of heterotic G2 system to the SU3 case, like with this circle bundle thing. Do you know what happens if instead of reducing on a circle bundle, you're reducing an SU2 bundle? Do you also have like a nice reduction thing where now you have maybe some SU2 structure below on a 4-dimensional manifold, and again you have some kind of heterotic Bianchi identity happening, or is it very important that it's like a 1-dimensional reduction in some sense?
Yeah.
Yeah,
I don't know if there is something already done in the literature in this direction, but I don't see why you don't do this, because you could have some one form. You can have a T3 bundle over
right.
some 4-dimensional manifold,
Mm-hmm.
and then you will have three connection one forms, for instance, and you can
Hmm.
write your G2 structure in this context and see what happened. Yes,
Yeah,
I
yeah,
think
I see.
it's something that can be
Yeah,
done.
yeah, I guess there are some examples of these closed torsion G2 structures on things that are just spheres and a lot of tori. Yeah, but I was curious, yeah, like, okay, yeah, I can see how with three tori it would work, but do you think it would even work if instead of three tori, I have like a sphere bundle, like an SU2 bundle, instead of having like something, that is just a billion? Do you think it would still work? Like a part of me wants to
Something,
think yes, but I don't know if it's,
something which is non-abelian.
yeah, like a principal bundle, which is an SU2 bundle, for example, and you use that to reduce instead of just a circle bundle. Like, I feel like maybe it should work as well, but I don't know if actually it's very important that you have a circle bundle and you have an abelian group. It's like a U1 thing instead of.
No, in some sense, you don't need to have just an S1 bundle. I mean, at the
Okay.
end, what you need is you have this SU2 symmetry in order to construct your G2 structure.
Hmm.
But
Right.
yeah, I think it's completely possible, yes.
Okay, I see. Yeah. Yeah, thank you very much. It's very interesting. Thank you.
Okay. Thank you for your question.
More questions?
Yeah, maybe I also have a question. Thanks, Andres, for the very nice talk.
Thank you.
So so you have some sort of results about long-term existence. Do you know anything about the singularities of the flow? What would you expect singularities of the flow to look like? What sort of generation might happen?
No, I mean that should be I mean I am very new in these kind of things. So I think the key ingredient that you need in order to study this kind of question is the She-type estimates, right?
Mhm.
And as far as I mean, we try to finish this very quick. So we didn't try to look at this kind of result. But yeah, I mean, what some important question is what is the solitons for this? Because there are no longer more the generalized Ricci solitons which are steady, right?
Mhm.
So probably there are other kind of solitons. So yeah, that is a future word. It
Okay.
should be very nice to try to look.
Yeah, I was thinking about something along the lines of maybe like your dilatant function, this conformal factor, maybe it blows up along some, I don't know, typically it blows up along some some hypersurface, so codimension one hyper like submanifolds, and then this have some sort of special structure, something along those lines. This is what I was but yeah. But we don't
Yeah,
know.
no,
Okay.
yeah, I don't know, but it should be very interesting to look at that.
Okay. Cool.
Thank you.
Great. Thanks.
More questions?
Sorry, may I ask again, now that you're showing this corollary, is there a reason for this gamma and sigma to be like bounded by these values? Is there any deep reason, or is just some technical
Yes. I
thing?
mean, I try to choose at least, yeah, no, it's basically because of the monotonicity of the dilaton functioning.
Mm.
It's because you have the monotonicity for these bounds, and because you need the She-type estimates, we have the She-type estimate just for the particular variable C.
I see.
So that's why I say that, I mean, in some sense, this equation, this dilaton flow seems to be very generic, because in some sense you are evolving by some He-type equation plus lower order terms.
Mhm.
But they have a very geometric meaning along this monotonicity of the G2 dilaton.
Yeah, I
So
see.
yeah, it's because of that.
Mhm. Okay, I see. So
Okay.
it's just a very technical thing, I guess, like that just the numbers come out this way, right? Like with, I guess if you put 4/3 there, that's what
Yes, yes, exactly.
right.
Yes,
I
yes.
see. Okay.
Yeah, you
Thank you.
just you just want to guarantee that the functional is monotony.
Yeah, no, makes sense.
Some more questions? So if not, let's thank Andres again for the nice talk.
Many
thank you.
thanks for the attention.
And I think that we may stop the recording. I don't know if I can do this, or maybe just